Hello, and welcome to this presentation, Understanding Frequency Counters. In this short presentation, we'll provide a technical introduction to frequency counters and common frequency counter measurements. Frequency counters are devices or instruments that measure the time interval between cycles of repetitive electrical signals. Common examples are sine waves, square waves or pulses, sawtooth waves, etc. The time interval between cycles can then be used to calculate other quantities, such as the frequency and the period of the signal. Counters which have multiple inputs can also compute quantities by comparing two different waveforms, such as the ratio of frequencies between two inputs or the time interval between two inputs. Results are commonly displayed numerically in real time, but most counters can also log values to a file. And although frequency counters only measure electrical signals, special devices called transducers can be used to count mechanical, optical, and other non-electrical events. There are many frequency counter applications. Most involve measuring or adjusting devices whose output is, at least nominally, frequency stable. Examples are oscillators, phase-locked loops, clocks, timers, etc. They are also used in measuring device output frequency, such as in radio or radar systems. As mentioned earlier, counters are most often used to provide absolute measurements of a signal, but can also be used to make measurements of a signal relative to another signal. And although frequency counters are primarily lab instruments, handheld counters are often used to determine the frequency of unknown sources in the field. One special application of frequency counters is measuring Allen variance or Allen deviation, which is a longer-term measurement of oscillator stability. By longer term, we mean measurements made over hours, days, etc. Frequency counters come in a variety of form factors, the most common being a benchtop or a handheld instrument. In almost all cases, the measurement results are shown directly on a numeric display, and the counter is controlled and configured using front panel buttons and menus. Note, however, that more advanced frequency counters can sometimes be operated programmatically. That is, the counter can be controlled and measurements can be configured via a USB or LAN connection. Most frequency counters have a standard BNC connector, although SMA connectors are often used for higher frequency inputs. These ports are usually connected directly to the device under test via a cable, but in some cases it's also possible to use an antenna to make over-the-air frequency measurements. Now let's look more closely at how frequency counters work. A frequency counter counts the number of rising or falling edges of a signal, where an edge is defined as the signal transitioning through a defined trigger level. These counts are performed and reported over a user-defined gate time. For example, here we counted 20 cycles with a gate time of 1 second, so the frequency of the signal is 20 Hz. In most cases, this gating and counting process is performed continuously, and other measurements or quantities, such as frequency or period, are derived from the gate time and count. Gate time can have a significant effect on measurement results. Generally speaking, longer gate times produce more accurate measurements. For example, using a gate time of 100 seconds, we count 2012 cycles, which corresponds to a frequency of 20.12 Hz. If we reduced our gate time to only 10 seconds, our measurement accuracy would fall to 20.1 Hz, and reducing it further to only 1 second, our counter would show the frequency as 20 Hz. Some counters explicitly indicate this change in accuracy by increasing the number of displayed decimal points as the gate time is increased. There is, of course, a trade-off involved in that longer gate time means that the measurement takes longer to complete. It's also worth noting that the gate time must be greater than one period of the signal in order to get a reliable measurement. Regardless of gate time, the inherent accuracy of a counter depends on two factors. The first of these is an accurate measurement of the gate time, that is, how long was the gate open. This is largely a function of the counter's time base, something we'll discuss in more detail on the next slide. An inaccurate or unstable time base can lead to a gate time that's either not known and/or not stable, which will affect the number of cycles counted. The second requirement is accurately counting the number of true cycles that occur during the gate interval. We want to be sure that we're counting every true cycle and that we are not counting non-cycle events, such as low-level noise or bursts of noise. Over the next few slides, we'll discuss in more detail the different methods for obtaining higher frequency counter accuracy. As mentioned a few moments ago, accuracy is very dependent on the counter's internal clock or time base. This is a highly stable internal oscillator that's used to determine the time intervals and thus the gate time. Time-based accuracy is commonly affected by temperature, and obtaining high accuracy requires that the time base be temperature controlled. One method of doing this is to have an oscillator that compensates for temperature changes, but the preferred method is placing the oscillator in a temperature-controlled environment, often referred to as an oven. Time-based accuracy can be further enhanced by using an external clock source, although clearly this assumes that the external source is more accurate than the internal time base. Atomic or rubidium-based clocks and GPS-disciplined oscillators are two very common sources of high-accuracy clock signals. Note, too, that time-based accuracy may degrade with age, so periodic calibration of internal time bases may be required. Another factor that affects accuracy is signal conditioning. Detecting true cycles is easier when the signal has an appropriate amplitude and is mostly free of noise. With regards to amplitude, best results are obtained when the amplitude of the input signal falls within the counter's input sensitivity range. This is typically done by adjusting the input level through either attenuation or amplification. This adjustment can be done manually, but many counters have an automatic gain control that performs this automatically. In the case of noise, filtering can be used. In frequency counter application, noise tends to be higher frequency than the measured signal, so low-pass filtering is used. This filtering can be implemented using either analog filters or by using digital or DSP-based filters. The last accuracy-related factor we'll discuss is trigger level and hysteresis. Recall that accuracy requires that all valid, but only valid cycles be counted, and that cycles are counted when they cross a trigger threshold or zero crossing. For example, here we increase our cycle count every time we see the waveform cross 0 volts. A potential problem can arise when noise or other effects lead to crossings that could cause false or incorrect triggering, such as the one shown here. This issue can be minimized by using something called hysteresis. Hysteresis is usually defined as a zone, and the signal must pass through both the lower and upper bounds of the zone before it's counted. Most frequency counters allow hysteresis to be automatically configured and enabled, but in some cases, hysteresis values can be user-adjusted to match the waveform properties. Next, let's go over the most common frequency counter measurements. These are frequency, period, total, pulse width, duty cycle, frequency ratio, phase difference, and time interval. We'll start with the most basic of these, frequency, period, and total. Frequency is the number of cycles per second and is measured in hertz. In this example, there are 5 cycles in 1 second, and the frequency therefore is 5 hertz. It's safe to say that frequency is the most fundamental frequency counter measurement. Period, on the other hand, is the time between 2 cycles. Period is measured in seconds and is the inverse of frequency. Total is the number of cycles seen since the start of the measurement. That is, it's the cumulative sum of all detected cycles. Pulse width and duty cycle are measurements that are only made on pulsed signals. Pulse width is fairly self-explanatory. This is simply the width of the pulse, given in units of seconds. Duty cycle takes the width of the pulse and then divides it by the period. The result is normally given as a percentage, which represents the percent of time that the signal is on. For example, in the diagram on the right, the period is 3 times the pulse width, and thus the duty cycle is 33.3%. Our last 3 measurements are derived from the simultaneous measurement of 2 signals, which we'll call A and B. Ratio is nothing more than the ratio of these 2 frequencies, and thus is a unitless number. Phase difference is a measurement of the phase offset between A and B. This measurement is only possible for square wave type signals, and the phase difference is normally reported in units of degrees. Time interval is similar to phase difference, except that it measures the difference between 2 channels in units of seconds. In many cases, this value is reported as the average time interval, rather than the time interval on a per measurement basis. Let's end with a brief summary. Frequency counters measure the time or distance between cycles in a repeating waveform, as well as quantities derived from these measurements. They're used in many different applications, from basic radio transmitter testing to more esoteric measurements such as Allen variance. Counters perform these measurements by counting the number of waveform cycles that occur during a user-defined gate time. Generally speaking, increasing the gate time improves measurement accuracy. Higher accuracy can also be obtained by using a higher quality frequency reference or timebase, by conditioning the signal in terms of amplitude and noise reduction, and by using hysteresis to avoid false triggering. Almost all frequency counters can report results in a variety of formats, including basic ones such as frequency, period, and total, pulse-related measurements such as pulse width and duty cycle, and measurements derived from 2 signals, including frequency ratio and phase difference. This concludes our presentation, Understanding Frequency Counters. If you'd like to learn more about this and other test and measurement applications, please see the links in the video description. Thanks for watching. Please subscribe to our YouTube channel and visit us at rody-schwartz.com.